The next chapter we begin in the semester is chapter 7, alkene structure and reactivity. So in this chapter, we are going to begin by taking a look at alkenes. Alkenes are hydrocarbons with at least one C double bond C. All right. So you're looking at molecules that have at least one pi bond. First, we're going to begin this chapter by taking a look at the structure of these molecules. And then we are going to go to the reactivity of alkenes. How do double bonded molecules react? All right. The key idea of this chapter is that alkenes are a class of unsaturated hydrocarbons that consists of C double bond C, at least one pi bond. As a result, rotation across C double bond C is restricted and alkenes undergo electrophilic addition reactions. So we'll take a look at this part of the statement in the second half of the chapter, but let's begin by taking a look at the structure of alkenes. Alkenes are unsaturated hydrocarbons. Anytime you have a pi bond, you will call them unsaturated hydrocarbons. Alkanes are saturated hydrocarbons. All right. So alkenes are unsaturated hydrocarbons. They contain double bonds formed between sp2 hybridized carbons. At each sp2 carbon, the bond angle is 120 degrees and the geometry is trigonal planar. Pi bonds in alkenes prevents rotation across C double bond C. Just to remind you of the structure of alkenes, if I take the simplest alkene, which is C2H4, this is the structure. Each carbon is sp2 hybridized. So the geometry around that carbon is trigonal planar, bond angle 120 degrees. Each of the carbon has one p orbital that is unhybridized. The two p orbitals have a lateral overlap, so you have the pi bond. So let me show you the structure. So here is the structure of C2H4. Each carbon is bonded to two hydrogens. These are sigma bonds. Single bonds are sigma bonds. In this double bond, you have one sigma shown by gray, and the other is the pi bond. All right. Now, if you look at the geometry at each carbon, all these three sigma bonds are hybridized. The geometry is trigonal planar. As you can see, they are resting on the plane of my palm. And the angle is 120 degrees between each of these bonds. All right. Each of the carbon has a p orbital left that is unhybridized. Those two are overlapping laterally to form the pi bond. A top overlap and a bottom overlap is one pi bond. All right. Now, because of this pi bond, there is restricted rotation across the C double bond C. I cannot rotate this because I have a pi bond here. All right. So the moment you put a pi bond, you can't rotate across carbon-carbon bond. All right. On the other hand, if I take a look at an alkane like C2H6, CH3, CH3, each carbon here is bonded to 3 hydrogen. Again, each carbon is bonded to 3 hydrogen. So this is an alkane. There are no pi bonds. All are single bonds. I can freely rotate. Okay. So that's what I mean by restricted rotation when you have a double bond. The moment you have a double bond, you do not rotate or you cannot rotate. Okay. So let's go back to the slides. So that is about the structure of alkenes. Most of you are familiar with these points. We have taken a look at them in chapter 1. Now the first concept you're going to learn in this chapter is degree of unsaturation, abbreviated as DOU. To simply define what is degree of unsaturation, it's nothing but the combination of a pi bond and a ring in a molecule. So every pi bond and every ring adds to 1 degree of unsaturation in a molecule, right? So if you count the total number of rings and pi bonds in a molecule, it will tell you the total degree of unsaturation in that molecule, right? So let me explain you this with the help of an example. Let's say I have this molecule and I ask you the degree of unsaturation in this molecule. As you can see, you have only one pi bond, so the degree of unsaturation here is 1. Let's take another example. How many degree of unsaturation in that molecule? 2 pi bonds, 2 degrees of unsaturation. Let's take a look at this molecule. How many degrees of unsaturation in this molecule? You have 3 pi bonds and 1 ring. That's a total of 4. So the degree of unsaturation for this molecule is 4. If I have this molecule, 2 pi bonds plus 1 ring, so the degree of unsaturation is 3. So as you can see, just by looking at the structure of the molecule, you can figure out degree of unsaturation. Count the total number of pi bonds and rings, and that will be the degree of unsaturation for that molecule. All right. Let's take one last example. What's the degree of unsaturation for that molecule? A triple bond has 2 pi bonds. So the degree of unsaturation here is 2. All right. So as you can see, given the structures, it is very straightforward to figure out the degree of unsaturation. But let's say I have not given you the structure, I have rather given you a molecular formula. How are you going to figure out the degree of unsaturation? That is when you're going to use these equations. When you have just carbon and hydrogen, that will be the equation you use to figure out the degree of unsaturation. 2 times the number of carbons plus 2 minus the number of hydrogens, the entire bracket divided by 2. If oxygen is added to the molecular formula, you can still use this equation. Adding oxygen will not change that equation. All right? If halogens are present, this is the equation you're going to use. X is the number of halogens. If nitrogen are present, this is the equation you're going to use, where N is the number of nitrogens. Now you don't need to memorize these equations. These equations will be provided to you during the exam. You will have them on the exam information sheet. But for us, it's going to be more important to figure out the degree of unsaturation looking at the structure. That is more important than going through these formulas. All right. So count the total number of pi bonds and the rings when you have a structure. That will be the degree of unsaturation. All right. So we'll end today's lecture here. Please let me know if you have any questions regarding today's lecture. Have a good rest of the day.